So like I said, there's a lot of similarities between what you have in front of you and what we just covered with proportions. There's really only a few differences. So we're going to go pretty quickly through these. That's why chapter 9, chapter 10, they go pretty fast. They go pretty fast because it's a lot of the same stuff, right? We know what a confidence interval is. We know what a hypothesis test is, those type of things. So remember, when do we use to sample? When the question is, are the two samples significantly different from each other? The samples come from two separate populations, right? So if the sample has if there's a significant difference, it'll tell us. That's what the test will tell us, or a confidence interval will tell us, right? As opposed to one sample, where one sample was just the sample, is it significantly different from the claim, whatever's claimed? Okay, the claim in these is always the same. The samples aren't any different. There aren't any different, or there's not a significant difference. There's not a significant difference, okay? So remember, we have Z or T. Most of the time, it's going to be T for means, okay? So what it does is it helps predict or estimate the difference in the two populations, right? If one Math 1 class took a test and the other Math 1 class took a test, and I took a sample of each Math 1 class and I did a confidence interval, this type of confidence interval, it would tell me it would estimate the difference in the two populations. Okay, that's what it is. The difference between the two proportions or population means. Okay, define parameters. We've done that before. That's not anything new. All conditions or assumptions are the same as in the previous, as in chapter 9, chapter 7, chapter 8, chapter 9. But just remember, we have to do 3 columns, one for each, right? One for each sample. Interval. So the interval will always be the difference. So the conclusion, there's always going to be the word difference in there because that's what they are. They're differences. Okay. Here's the formula we're going to use for two sample T. I only put the T one up there because that's usually what we have, but you could use it for Z as well, right? So subtract the two means, or the two sample means, right? Plus or minus T critical, and then where is it? There you go. And then the standard error, right? That guy is right here on your formula sheet. They put it for Z, but you can just change those to S, right? Okay, each one of them squared over how many in the sample, add them together, take the square root. Okay, so very similar to that. Okay. All right. Okay, so let's do one. Let's go ahead and skip ahead to, I think, example number 2. Example number 2. Yes, example number 2, Justin Timberlake and Katy Perry. Students wondered whose Instagram account gets more likes on average, Katy Perry's or Justin Timberlake's. So the students selected a random sample of 15 Instagram posts from Katy Perry and a separate random sample of 15 Instagram posts from Justin Timberlake and recorded the number of likes for each post. Here are the dot plots. Okay, so this is real data. I didn't come up with this data. It's actually a student came up with this data. They did 15. They randomly picked 15 posts from Katy Perry and then randomly picked 15 posts from Justin Timberlake. And then they documented how many likes at that time, how many likes, right? They got, and then graphed it, and then gave me the means, the sample mean, and standard deviation. Okay. So each one of the dots for Katy Perry represents a post. How many likes they got on that post. Same thing with Justin Timberlake. And then the sample data over there. Okay, so what we have to do with the data is construct and interpret a 95% confidence interval for the difference in the mean number of likes for Instagram posts from Katy Perry and Justin Timberlake. Okay, so we're looking for the confidence interval for the true difference between them. So if I had all of the posts, if I went through every single one of Katy Perry's posts and found out how many likes for each one, and same thing for Justin Timberlake, and subtracted them, that's the number, that's what I'm trying to calculate. Okay? Okay, so confidence interval. Confidence interval, always start with population parameter. We have two populations. So population parameter, since it's means, we start with mu. True mean number of Instagram posts for Katy Perry and Justin Timberlake. So one is going to be for Katy Perry and one of it is going to be for Justin Timberlake. Okay. I forgot. We want to label each one of these. So, because we're going to have two of these. So you can put sub 1, or it'd probably be easier to put sub KP for one and sub JT for the other. Mean number of Instagram likes for Katy Perry. All right. That's the first one. The second one is the only difference is true mean number of Instagram likes for Justin Timberlake. Okay. That's the population parameter. Okay. Next thing is, let's see, test statistic or let's do test statistic. Which test statistic am I going to use? Okay. Well, I'm going to use the one I just saw. Okay, right there. It's T because I don't know the true standard deviation for either of them because I only know 15 they only took a sample of 15. So I don't know the true standard deviation for Katy Perry or Justin Timberlake. All I know is the 15 that were randomly selected. Okay. All right. So let me write that down. X bar KP minus X bar JT. So you don't want to use 1 and 2 anymore because they don't mean 1 and 2 anymore. You want to stay consistent. Just stay consistent through the whole thing. Okay. Plus or minus T critical times. But can we still label them like 1 or 2 if we want to? So if you said JT and KP, and then you put down here, you put 1 and 2, that would be wrong because if you put JT and KP and JT here, and then you switched it back over here, that's confusing. Which one are you talking about? Are you talking about, so just stay consistent through whatever you choose all the way down. Whichever way you choose, just stay consistent. The reason I changed it to letters instead of numbers is because let's say I did 1 and 2. And then I get down to the calculations. And then I'm like, wait, which one did I pick for 1? Which one did I pick for 2? It's easy to kind of, you have to go back. And it's kind of easy to make mistakes there. Whereas if I label them KP and JT, I'm less likely to do that. Okay. So just stay, like if you pick 1 and 2 here, if you put 1 and 2 here, it's okay, but just stay consistent, okay? All right, so standard deviation for the first guy, squared, and then n kp plus jt over n jt. Okay. So if you choose to use 1 and 2, just stay consistent. If you choose to label them like I did, stay consistent. Okay. All right, so now we have conditions, assumptions. So we're going to have 3 columns. Let's see. So the first one is going to be for KP. So check X bar KP. And then check for JT. Oops. Okay. Because they're 2 separate samples. They were gathered separately. They weren't gathered together. Okay, so one is SRS. How was that gathered? So it says a simple separate random sample. So stated. Okay, 2 is 10% condition. Okay, oops, 2. N is less than or equal to 10% of big N. Okay, so N for each of these was 15. Okay. If little n is the randomly selected 15, big N would be all of the posts. All KP Instagram posts. All JT Instagram posts. Okay. So that number would have to be more than 150. We don't know it, so we can't check it. That's the best we can do. Okay. Number 3 is shape. Approximately normal. Okay. So for this condition, remember, it's different than n times p, n times 1 minus p. That's only for proportions, yeah. So I believe I put it in here just to remind you. It's in your notes, but I put it in here. Conditions. So we have 3 options. Population stated as normal in the question. I don't think they said that. N is greater than 30. So central limit theorem. Central limit theorem. In other words, each, not combined. So each of them is greater than 30. That's not true. We have 15 and 15, right? So we have to graph both sets of data and look for any outliers. Well, luckily they already graphed it. Luckily, the data came with a graph. So we don't actually have to graph them. We just look at the graph and just look to see if there's any outliers, if there's any numbers that are, Katy Perry does not have any outliers. So, so that one's not okay. So this one, Justin Timberlake has a bigger standard deviation. You can see a bigger standard deviation right here, right? Because his dots are a little more spread out. Okay, so let's look at some of the dots. This dot over here is how far on average is this dot away from the next closest one? Because I know a lot of times when you're looking at these, you look at, oh, there's some area there. That guy is an outlier. So what would this guy represent? What would this guy I circled around? How many around? What would he approximately would represent around 13,000-ish, right? What is the next biggest one? Around 11,000, right? Around 11,000. When you're talking about thousands, is 2,000 a lot? Is it not a lot? I don't want to say a lot. Crazy big. Is it crazy big difference? Right? Because outliers mean crazy difference, right? I know there's a difference between those guys. There's definitely some distance between them, but for outliers, we're looking for crazy distance between them. That's not a crazy distance, right? If this number was like 40,000 and we had a dot over here, I would say that's crazy, right? That's like 30,000 more, right? That's a little bit, that's drastic, right? That's what we're looking for outliers. So I don't think any of these would consider like crazy big or distances, right? The distances here are not crazy. This one's probably the biggest distance here from 5,000 to like 8,000. But again, you're talking thousands. So that's not really that much. You got to think in terms of, in terms with, and you got to put perspective in there to see if it is. So there, I wouldn't say there's more spread. His is definitely more spread out, but are there any dots that are just crazy big or crazy small? Nah, I wouldn't say that. Okay. So we would put graph shows no outliers. Same thing here. Graph shows no outliers. Right? Because an outlier is something that's crazy big, right? Crazy difference. Okay. Okay, calculations now. Okay. So first thing we're going to do is we're going to subtract the means. First thing we said we were going to do is subtract KP minus JT. So we're going to go to the top and we're going to subtract this guy minus this guy right here. 7193 and 6393. Plus or minus T critical. So remember, anytime we're using T and we need critical, we need a degrees of freedom. Right? We didn't talk about degrees of freedom for two sample. For one sample is n minus 1. For two sample, if you go in the notes, there's two ways to do degrees of freedom for two sample. One is take the smaller sample and go n minus 1. The calculator will also do it for you. If you really want to know the exact degrees of freedom, this is the formula here. That's the formula here. But the calculator does that automatically. That's not a formula you need to know. But for some people, they're like, well, what is the degrees of freedom? Is it this or is it that? Because you're going to get two different numbers. N minus 1 will give us one number. The calculator will give us another number. And people are like, why is there a difference? Why is there a difference? Well, the calculator uses this guy. We approximate using n minus 1, smaller n minus 1. Okay? So when we use the calculator, it's going to give us degrees of freedom. And it's going to be different than the one we approximated with. It's okay. It's okay. So n minus 1, so it'd be 14 degrees of freedom. 14 degrees of freedom for a 95% confidence interval.
How would that work for this one, since there is no smaller sample?
They're exactly the same size. So we would just pick one. Yeah, we would just pick one. Yeah, there is no smaller. So we would just pick one of them. 15 minus 1 is 14. Yeah. Okay, so 14 degrees of freedom. And we have a 95. So 95 is right here with 14 degrees of freedom. That's the guy we're going to use. 2.145. 2.145. Okay. (15 minus 1 equals 14). Okay, so underneath we have standard deviation for the first one squared. Katy Perry standard deviation. So 1,749 squared. Over how many in her sample? The second one, Justin Timberlake standard deviation. 3,470. Squared, and he had 15 in his sample size.
It's 1,749.
Did I use the wrong one? 1,749. Yep. 1,749. Okay. All right. Crunch that by hand, or we can use the calculator to determine the interval. Okay, so you should still be able to do this by hand, because on some multiple choice, you've seen on multiple choice where they want you to calculate that by using just the calculator. You're not allowed to use, because they'll say which one matches, they'll go this plus or minus this, which one matches that guy. So calculator's nice, but the calculator sometimes won't answer every question, especially the multiple choice ones. FRQ you're fine with, but multiple choice sometimes they want you to actually calculate that separately. Okay. So we go stat, S, down to interval. We want a 2. We're doing a T interval, and we want 2. So the only one that has 2, T, and interval is number 0 after 9. That's the only one that has all 3 of those. So that's the one we're going to use. So again, it asks us, hey, do you have the data in L1 or L2? No, we don't. So we're going to go stats. So we're going to put the standard the first sample. So Katy Perry sample mean 7193. For standard deviation, 1749. Next one, Justin Timberlake. Did I put the wrong one?
No, that's sample size.
Oh, sample size. Sorry, 15. 6393. 3470. Sample size 15. Confidence level was 95%. Pooled, nope. Remember, the only time we pool is for proportion tests, 2 sample proportion tests. Only time we pool. It'll always ask you this question too. And most of the time you're going to say no. right? We only do it for 2 proportion tests. The notes we did on Wednesday, Tuesday and Wednesday. Okay. There we go. So the first thing is the degrees of, or sorry, the first thing is the interval negative 1,288 to 2,888.5. Okay. Right underneath there is the degrees of freedom. That's the more accurate degrees of freedom, right? We used 14. More accurately would be 220.68, so on. We approximated it, okay? How did they get that number? They used the formula I gave you. You don't have to use that formula ever, okay? You either approximate it or you use the calculator, either one, okay? But that's how they got that, because I always have some people say, well, why did we get 14 and they got 20? And it's just approximation, okay? That's the data we put in. Let's see, is there anything else in here that we could use? Nope, that's it. Okay. So let's stop right there. The interval, before we do the conclusion, what are we looking for anytime we do a 2-sample interval? What are we looking for in the interval to see if 0 is in the interval, to see if 0 is in the interval, right? If 0 is inside the interval, that means there's a chance that both are the same. That there's a chance that there's no difference between Katy Perry's likes, Justin Timberlake's likes. It's possible they have the same number of likes, right? It can be a little confusing because you go up here and you're like, well, they didn't have the same number of likes, right? Katy Perry had more average than Justin Timberlake. Yeah, there is a difference in their samples, but it wasn't a big enough difference to say, on average, Katy Perry is going to have more likes than Justin Timberlake. It could be just in that sample of 15, there happened to be more, right? Sampling variability. I could take another sample and Justin Timberlake could have more in those than Katy Perry. Okay? That's what our interval says. Our interval says there's not enough difference in the samples to say that Katy Perry has significantly more. How do I know that? Because 0 is inside there. 0 is inside the interval. Now, if this negative wasn't there, then you have something. 0 is not in the interval, right? So Katy Perry has significantly more than Justin Timberlake, right? If that negative wasn't there. But that negative is there, so okay. So even if they don't ask you that question, it's still important, because it's still important to that's the idea behind why we do this confidence interval. Okay? We're looking for 0. Is 0 somewhere in there? All right. Okay, so conclusion. We are 95% confident that the true the true difference in mean that's the key word here, difference in mean Instagram likes for Katy Perry and Justin Timberlake is between negative 1,888 and 2,888.5. So could Katy Perry have more likes on average than Justin Timberlake? Yeah. Could Justin Timberlake have more likes on average than Katy Perry? Yeah. How do I know that? Because zero's inside the interval. Zero is inside the interval. Okay. Let's see. Is there another question that goes with it? Or is that it? Nope, that was it. Okay, so that's confidence intervals. Okay. Let's go to hypothesis tests. Hypothesis test. It's the second page. Top of the second page. So again, two samples, Z and T hypothesis test for means. When testing the hypothesis, there is no significant difference between the two samples. There's no significant difference. That's always going to be our null hypothesis. The null hypothesis will always be there's no difference between the purport. We're trying to disprove that. We're trying to reject that. Parameters and conditions are the same as confidence intervals. So it's the same three conditions we just did. No pooling is needed. You don't need to pool. So you always say no for means. The only time you do it is for two sample proportion tests. Two sample proportion tests. Again, both of these guys are very popular on tests for FRQs. Almost every FRQ you see for the last 10, 15 years that has to do with this that has to do with confidence intervals and hypothesis test is two sample. It's the one we use most in life, in research, right? I talked to you guys the other day about, doctors when they're trying to prescribe, when they have new medications they could prescribe to their patients, right? That's how they do it. They look at they read medical journals, and in medical journals are hypothesis tests and confidence intervals, comparing what we did before to what we do now. Is it better? Is it significantly better? Because if it is, use that new procedure, use that new medication, use that new whatever, right? If it's not, then why change? Okay. Two sample. So they do it a little differently. It's the same thing as what we do, right? It's the same thing. You can write it like this, or you can write it like this. 1 equals 2. Either one. They mean the same thing, right? If one is equal to the other, then when I subtract them, I should get 0, right? So it's just different. One is not better than the other. They accept both. Either one is okay. But I'm just, from wherever I got this, that's the form they use. They said, if you subtract them, they get 0. Well, that's the same thing as saying they're the same size. Okay, and then we have 3 options. Greater than, less than, not equal to. Same as always, right? I only put T because most of the time it's going to be T. So on top, again, we subtract the means, and then we subtract it from 0. Why 0? Where does 0 come from? The interval and the null hypothesis, right? The null hypothesis, the claim from both places, right? But if you subtract something from 0, does it really matter if you subtract it? Yeah. So most of the time you won't see that, but I put that on there just to know it's supposed to be there, but it doesn't matter because if you subtract 0, it's going to stay the same. And then the bottom's still the same, right? The bottom's the standard error. Conclusion's the same. Okay. Okay, let's try to get through this and then we'll be done for today. So last question, example number 3. Example number 3. Okay, so what I want you to do is underline, highlight, circle right? Anything that's important. So read it. It's a medical experiment, results of a medical experiment. Okay. The number one, how do I put this without being too morbid? The number one reason, so the reason why people die, the fatality rates, the number one on that list is heart disease. Heart disease. That's the biggest reason why, the biggest cause of death in the United States is heart disease, right? Bigger than disease, bigger than cancer, bigger than anything else, right? The number one is heart disease. So blood pressure is extremely important. When you go to the doctor's office, and they call you back and you sit down, what's the first thing they do?
Test your blood pressure.
Blood pressure every time. Every time, maybe your temperature too. They'll weigh you, they'll take your height sometimes. Always blood pressure because of that. Because they know that's the biggest thing. Even if you're young, still check your blood pressure, right? Every time my sons are 6 and 8. They check blood pressure. They check your blood pressure first thing because it's a sign of other things. It could be a sign of other things. So so one of the biggest things in the health field is heart disease. So they're always trying to find, is there new ways to cure, or to not cure, you're not going to cure heart disease, but is there better ways to avoid it, so that you don't have to worry about heart disease? Or if you have it, is there better ways to treat it? Okay, so that's what they're doing here. So they're trying to see if there's a relationship. So they know of a relationship, right? There's a correlation between calcium intake and blood pressure, right? Correlation means if there's a relationship. It looks like if I give a patient calcium, they're more likely to have a lower blood pressure, right? That's correlation. Causation is what we're looking for. The only way to do causation, the only way to say, if you take this, this will happen, is by an experiment, which they did, right? That's the only way. So that's what they did. They see there's a correlation here. Hey, as this goes up, this is starting to happen. Interesting. So then they do experiments. So they did an experiment. Such observational studies do not establish causation. So researchers therefore said, you know what? We want to see if this causes this. If you take this, will it lower blood pressure, or help with that? Okay. The subject, so there were 21 healthy men who volunteered to take part in the experiment. They were randomly separated into two groups. 10 of the men received a calcium supplement for 12 weeks, so a pill. They got a calcium pill. Okay. While the control group of 11 men received a placebo that looked identical. So nothing. There was nothing in the pill, right? Nothing that was going to help them or hurt them. Sugar pill, water pill, those types of things. Okay. The experiment was double blind. What does double blind mean again?
Neither the researchers know what's been given and neither the participants.
Exactly. I don't know if I'm in the experiment and I'm taking it, I don't know which one I'm taking. If I'm giving you the pill as the nurse or whoever it is, they don't know, right? They're just told what to do. Usually because when you're in these experiments, only one person knows identities, right? You usually have a number or you have a letter to identify who you are, right? Because they don't use names or anything to affiliate with you. Usually one person in the experiment, the person who doesn't have any contact with anybody, will know who's who, right? It's a pretty big deal. Usually that stuff is kept under wraps. Your name, your actual name, and all your details, because they don't want to influence the results in any way. Okay? The response variable is the decrease in systolic. That's the top number. When you do blood pressure, this over this, that's the top number. Systolic blood pressure for a subject after 12 weeks. Okay? So any increase appears as a negative number. So when there's a negative number, that means there was an increase in blood pressure after 12 weeks. Blood pressure went up. If blood pressure goes up, that's bad for the heart, right? The higher the blood pressure, the more work your heart's having to do, which is not good in the long run. Okay? So group A. Group A, calcium. So this is the calcium group. This is the treatment group, right? So the first person, 7. The first person, 7. What happened to their heart rate after 12 weeks, or their blood pressure after 12 weeks?
Went down by 7.
They went down by 7, right? They went down by 7. The next person, theirs went up by 4, right? Theirs went up by 4 systolic, okay? Millimeters of mercury. The blood, and then the same thing. This person's went up. This person's went down by 12. Okay? Okay, so that's that. So what we have to do is show evidence or provide convincing evidence, test, that the calcium supplement reduces blood pressure more than a placebo on average for subjects like this one, right? Experiment's already been done. We have to analyze it. We have to do the analysis of it, okay? Which if you read, if in college, you'll have to, depending on what avenue you go into. But if you do something in STEM related, you're more than likely going to have to read some sort of journal where, you're reading for, what did they find? The statistics is always at the end, but that's what everyone flips to. First couple pages is what you did. What did you do? The first couple pages will be this stuff up here. And then as you read, you go to the back, and then that's where all the statistics are. That's the stuff you always go to. Okay. Okay. So tests. So we have 2 groups, right? So it's means, average. So we're looking here. So I'm going to say C for the first one, calcium for the first group. So it's going to start true, mean, what did we measure? What are they measuring? Blood pressure, systolic blood pressure for those who receive a calcium supplement. That's the first one. The next one was the placebo group. So it's going to be the same thing. True mean systolic blood pressure for those who did not receive a calcium supplement. So the only, should put did, who did. Okay. All right. Hypotheses. The null. They're the same. There is no difference in those who take the calcium versus those who don't. Their blood pressure is the same or not significantly different. No significant change. This one can kind of be a little tricky sometimes. We have 3 options. Not equal to. Not equal to is the one you always want to go to because it's the one that's just different, right? But that creates a higher p-value. So you only want to do that one when you have to. So let's see. In the question, which way are they want us to test? More than. They said, is there evidence that calcium reduces blood pressure? Reduces blood pressure. So if calcium reduces blood pressure, which one should be bigger? P or C?
C.
If calcium reduces blood pressure.
Oh, yeah.
P, right? That's what they want us to test.
But doesn't it want you to test whether it reduces it more than the placebo does? So wouldn't it be the other way around?
let's see. That a calcium reduces blood pressure more than
Yeah, right. Yeah, it should be calcium. Yeah.
so if it's gonna reduce
If an increase appears as a negative number, it says.
increase appears. Oh yes, you're right.
So
Yeah, that's right. I forgot about that.
Increasing the number.
That's right. Yeah, because an increase it's kind of opposite. Yeah, that's right. It's opposite of what you normally think. An increase means a negative number. So actually it's going to be the reverse, yeah. Because of that, the way they did it. So an increase would actually be less. Yeah. Alpha level, 5% since they didn't tell us what to do. Okay. We're running a little low on time, so we're not going to finish this, but I want you to do conditions assumptions right now. Do conditions assumptions, and then we'll finish the rest tomorrow.